Okay, so shall we start? So we're happy to have Xinyu from next city. He's gonna tell us about hidden symmetry for the gauge theory.
Thank you for the introduction, and thanks for giving me this opportunity to talk about my recent work. We know that quantum field theory is the modern language for describing various phenomena in particle physics, condensed matter physics, and cosmology. And in this development of quantum field theory, symmetry plays a fundamental role. It governs the formulation of physical theories, and it can characterize different physics structures of models, and it also simplifies the computation of physical quantity. This slide is a very brief review of symmetry in quantum mechanics. For every transformation, we associate a unitary operator, and it maps each operator O to U inverse OU. And this is a symmetry transformation if the Hamiltonian is invariant. Sorry, this should be the ordinary edge. And this means that the Hamiltonian commutes with this unitary operator U. And it was known in 1939 by Wigner that the set of all these symmetry transformations form a group. And if the group elements depend smoothly on a set of continuous parameters, then this group is a Lie group. And infinitesimal symmetry is characterized by its Lie algebra. But over the past decade, the notion of symmetry has been refined and generalized in many interesting ways. Now we have higher form or higher group symmetry, we have subsystem symmetry, we have non-invertible symmetry. An important lesson from all this development is that not all symmetries are described in the framework of group theory. And in today's talk, I will study a class of four-dimensional gauge theories and introduce a different type of symmetry that also cannot be fit into the framework of group theory. This is based on my work in progress with Enrico Antil, Panoberto Elipomodi, and Costa Sobos. Let me first introduce our players. We start with the N-4 Sukuyama theory, which is most the symmetric quantum field theory in 4 dimensions. And its field content consists of the gauge field A, the complex real spinors psi, and the real scalars phi. And in this talk, if I write it as 6 real scalars, I always use the lower case. And if I combine it into complex scalars, I use the capital letter. And there are 3 complex scalars, and I denote them by x, y, z. All these fields transform in the adjoint representation of the gauge group. And in this talk, I take the gauge group to be SUN. And here is the Lagrangian written in N1 superspace and also in components. This N4 Sukuyama theory is invariant under the N4 superconformal symmetry, which is characterized by PSU22/4. And its bosonic part contains the SO4,2, which is the conformal symmetry, and also the SU4, which is the asymmetry. Under this SU4 asymmetry, these fields transform in the representation 1, 4, and 6. And in particular, I write the transformation for the scalars. If we combine 6 combine scalars in this rank 2 antisymmetric representation, then the transformation is written like this. And it's straightforward to show that this RAB acts on the action equal to 0, which means that the action is really invariant on the SU4 asymmetry. And in this angle force Superyamil theory, we have local and non-local observables. But today we will focus on the simplest one, the gauge event single trace operators. Here for each set we can choose from the derivative act on f of psi of phi of psi bar of f, the f equal f minus for all these choices. And following Minahan and Zhang, it's useful to map these single trace operators to a cyclic GSU22/4 supersymmetric spin chain. So for each this W1 up to WL, we put it on a cyclic spin chain. And this is for the gauge event operators. We can shift the order. This W1, W2 up to WL is the same as W2, W3, WL, then W1. But sometimes it's also useful to consider open chain states, and they correspond to non-gauge event operators. We do not take the trace anymore. And from this angle force Superyamil theory, we can perform the orbifolding to get a family of angle 2 superconformal field theories. This orbifold is with respect to a finite subgroup gamma of SU2 inside SU4. And this is the general strategy. And the important result is that the angle 2 theory is a quicker gauge theory whose gauge group is a product of SU groups. And the coupling is given by this.
Is it conformal?
Yeah, it's conformal for angle 2.
Oh, I see.
Yeah. Actually, you can take finite subgroup gamma to be arbitrary subgroup of SU4, and you will get angle 0 or 1 or 2. But in general, for the others, they are not conformal. But for angle 2, it's still conformal.
I see.
So, yeah, today I will always talk about the simplest case.
So this is D3 brane probing singularity?
Yeah, D3 probing a singularity. And this orbifold superconformal field theory is invariant on the angle 2 superconformal symmetry SU22/2, which is a subalgebra of the GSU22/4. And in this theory, if we want to construct gauge invariant single trace operator, it's given by this. We start with the operator in angle 4, and then we act on it by the orbifold projection operator to project it to the gamma invariant part. And we can have a further twist. When this is identity, it's the untwisted sector in angle 2. But we can also have non-trivial twist. This will give the twisted sector. In the string language, this twisted, untwisted, and twisted is can be literally understood in the string setup when we perform the orbifold. And because this angle 4 theory and the orbifold theory, they are just different theories. So if we consider correlation functions in both theories, they are of course they are different. But it's very interesting that in the planar limit, all correlation functions of the untwisted sector operators in the orbifold theory are the same as those in the angle 4 Superyamils up to a gauge coupling scaling. This result was proved in 1998 using string theory perturbation techniques and using careful Feynman diagram analysis. But we know that these techniques are not always not always perfect for analyzing some special problems in planar limit because they can hide some symmetry. And in particular, we will see that this result, the matching of the correlation function in the orbifold theory and in the angle 4 Superyamils is really a surprise from the point of view of symmetry. focus on the simplest correlation function, meaning the two-point function, and in the simplest orbifold theory, which is the Z2 orbifold. So let's first introduce the simplest correlation function.
So this is equivalent to gauging this discrete group.
What?
Gauging the discrete group.
Yeah,
It's the same thing.
yeah.
So you need the discrete group has no to alignment.
Well, there's no anomaly for this theory.
Yeah, this is true.
Yeah, we will not consider the most general operators. We will only consider operators in the scalar fields without derivative. And we can have some linear combination of them. This naturally maps to the a spin chain state in SO6, in a SO6 spin chain. These correlation functions contain UV divergence and need to be regularized and renormalized. We can choose an arbitrary basis of this spin chain, and there are 6 to the L states. And we choose this for the Bayer operators. The renormalized operators are their linear combinations in generally. And in this discussion, multi-trace operators are expressed in the planar limit. And this operator in the SO6 scalar sector will not mix with other operators at the one loop order. And we can, from this Z, we can compute the mixing matrix and its leading contribution up to, and we call the leading contribution to be H up to an overall factor. And this H can be regarded as the Hamiltonian of a spin chain acting on this space. And there's the length, this spin chain system of length L. And for each one, we have R6. And if we diagonalize this 6 to the L times 6 to the L matrix, we get this eigen states O hat A and eigenvalues gamma A. And from this data, we can obtain the two-point functions. Take this simple form, and here gamma A is just the anomalous dimension. In the planar limit, this Hamiltonian coincides with the Hamiltonian of an integrals model that can be solved by beta lambdas. This was first shown by Minahan and Rambo in 2002. And from their result, it's useful to write it in terms of projectors like this. Here are this pi. Here we have 3 pi's. There are 3 projection operators on onto the singlet, the antisymmetric representation and the symmetric traceless representations of this decomposition. So because each one, we have for the spin chain for this system, we have a spin chain system, and each interaction is nearest neighbor. So it acts on 2 sides, because each side we have 6. So with 6 times 6 is decomposed into 1 plus 15 plus 20 prime. So we write the interaction in this way in order to make the symmetry manifest. This is the old result. Then we consider the amplitude theory, and as I mentioned before, we take the sequence example, which which has gamma equal to Z2. And for this theory, we just start with the N24 theory, N24 to be Mills with gauge group SU2N. And we truncate the N2 vector multiply and hypermultiply in this way. for fields in the vector multiplied, we keep the diagonal elements. So A1 is in the like A1 and Z1, they are in the adjoint representation of the first gauge group, and A2 and Z2 they are in the second. And for the states in the hypermultiplied, we keep the off diagonal part, and they transform in the bifundamental representation of SUN1 and SUN2. And in order to make the theory super conformal, actually decouple in one factor. For this theory, there's Z2 automorphism, which switch the indices 1 with 2. So in the quiver diagram, it looks like this. And our convention is that this x1 means that it maps from SUN1 to SUN2, and if it's 2, it's from 2 to 1, and similar for y. If after this orbifold procedure, we have two couplings G1 equal to G2. But in angle 2 theory, since the beta function for each gauge coupling vanishes, G1 and G2 can be varied independently while still preserving the angle 2 superconformal symmetry. So we introduce a parameter kappa, which is G2 over G1. And kappa equal to 1 is called the orbifold point. And in the limit, kappa goes to 0, the vector multiplied of SUN2 becomes free and completely decoupled from the rest of the theory. And this becomes a flavor node rather than the color node. And this theory will become the angle 2 superconformal QCD. And from a state in angle 4 Silver-Yang-Mills, something like this, we can get two angle 2 states by describing we just label it by a single integer 1 or 2. This index is called the dynamical index, and it's the it's the gauge group of the first field, like the first gauge group of the first field. For example, we start with some state like x, y, z, y, something like this. We index 1. The first one will be x1, and it transforms into fundamental of 1 and anti-fundamental of 2. And for the next one, in order to make it well defined, this must be a fundamental in 2. And then y2 will, and so we determine this index to be 2, and next can only be 1. Then for the z, this is already 1, so next can only be 1. And z is in the adjoint representation, which in the larger limit is fundamental times anti-fundamental. So this is also 1, and so on. So we see that all the color indices will be shifted after passing an x or y, and remain the same after passing z. So we only we can always specify an angle 2 state by angle 4 state with one dynamical index. And then we focus on the asymmetry rather than the whole superconformal symmetry. Every step I make it simple. So the unbroken part of asymmetry is this. Actually, SU2 plus U1. This is the inside SU22/2 of the angle 2 superconformal algebra. But for the Z2 case, there's an actual SU2, and these unbroken generators take this form. It can be R34, R43, and R33 minus R44. And for this one, it's R12, R21, and R11 minus R22. And this U1 is R11 plus R22, which is same as minus R33 minus R44. So these are the quantum numbers for each symmetry. So, from the group theory point of view, this SU4 asymmetry is decomposed into this SU2 left plus SU2 right plus U1. And all the representation we have before, 1, 15, and 20 prime, is decomposed in this way. A priori, in the study of angle 2 theory, we only have these representations, and for this we have 3, 1, 1, 0 state. Although they are coming from the same, although they are coming from different angle 4 multipliers, they should mix on the renormalization. And similarly, we have this 2, 2, 1 and 2, 2 minus 1. They can also mix. And if we consider if we consider H, which is the Hamiltonian, also it gives the enormous dimension. The result should be written in terms of SU2 left plus SU2 right plus U1 projectors rather than SU4 projectors, because we don't have this symmetry. But from the result before, for all the correlation functions already they already match, and for this special case, it should also match. And the result we see that the Hamiltonian of the orbifold theory is exactly the same as before. In particular, there's no splitting of SU4 asymmetry representations into SU2 left plus SU2 right plus U1 representations. So how can this be possible? We suggest that the simplest possible explanation is that the broken generators of SU4 are actually not lost. So let's look at the broken generators. There are 8 broken generators, R1, like RAB, where A takes 1 or 2, and B takes 3, 4, or the opposite. These generators are not defined in angle 2 theory. For example, in angle 4 supernomials, X and Z, they are related by this relation. We can map from X to Z by R to 3, and Z to X by R3 2. This is fine in angle 4 supernomials because both X and Z are in the adjoint representation of the H group. But after doing the orbifold projection, two sides, this X and Z, have different class structure. X is in the bifundamental representation, and Z is in the adjoint representation. So naively, this just doesn't make sense. To revival the broken generators, we upgrade all generators so that they are allowed to act not only on the internal space, but also on the color space. And here, in order to make the notation nicer, we define tau minus to be R23, and it's upgraded to tau hat minus, and similarly for tau plus and tau 3. And then we can just define the transformation rule for single particle space. Here's there's no any physics. We just define it in this way, so that originally it mapped in M4 it mapped X to Z, and now we just upgrade the generator and put a diagonal index I here everywhere. And of course, they satisfy the standard commutation relation. And we see that here, this, if you are more like mathematically oriented, it's actually not SU2 anymore. We have the algebra structure. But using this, we can upgrade the other generators and define the transformation rules in a similar way. So these are just the definition, but we need to know whether it makes sense. These upgraded generators are not really satisfactory because a broken generator will transform a well-defined multi-particle state like x, z, x, like x contained here, for example, x on x, y. And if we transform to z1, and originally this state is well defined, but this is not because z1, z2, this is not well defined. The color, because this is in adjoint representation of H group 1 and this is in adjoint representation of H group 2, so they cannot connect. And there's a natural way to resolve this problem. We just shift all the color indices afterwards. Here, if we replace this 2 by 1, like we act on x, this x, and make it into z. And then for the others, if we can shift all the color indices here, this 2 becomes 1, this also becomes 1, shift everything afterwards, then of course we will get a well-defined state. But the result of this shifting is that the action of upgraded generators cannot be local in the sense of spin change. But this is possible. Here I will briefly introduce some mathematical structure. We will assume that the full Hilbert space is decomposable in this way. We have the 0 particle state, which is the vacuum, and the 1 particle and 2 particle, and so on. And the symmetry transformation acting on the 1 particle Hilbert space form a Lie group G with Lie algebra G. And to describe the symmetry transformation acting on the 4 Hilbert space, we introduce the universal enveloping algebra U of G. And basically it's the direct sum of the tensor product of G mod out by the commutation relation of the by the commutation relation of the Lie algebra G. And for this universal enveloping algebra, we can equip Hopf algebra structure by defining the following 5 maps. First we have the product which maps 2 elements in the universal enveloping algebra into a third one. And this allows us to multiply generators. This is important because for the original Lie algebra, we only define the commutator. For example, xy minus yx is defined, but for each individual one, x times y and y times x, they are not defined. But in the Hopf algebra, in this universal enveloping algebra, we can define this product and make sense of x times y. And second is the unit. Basically, this assigns the unit element with respect to this product. The more important one is the coproduct, which maps an element at inside U of G into the product of 2 U of G. And this means that if we know the action of the symmetry generator act on 1 particle state, this will give us the action on 2 particle state. And if we repeat this coproduct, we know how to handle states in all the more particle Hilbert space. And then in order to define the vacuum, we introduce the co-unit. And finally, for the antiparticle, we have the antipole. And for these 5 maps, there are some compatibility conditions, but we will not discuss here. So, for a classical symmetry, which we usually say that the theory has some symmetry on the gauge group G, under some group G. What we mean is that for multi-particle states, we take this simple relation for the coproduct. It's the simple Leibniz rule. We first act on if we consider the action of a symmetry generator on 2 particle states, we first act on the first one and keep the second in mind, plus act on the second one, keep the first one in mind. This is the usual way we take. And for the others, it's the standard choice. But in a quantum symmetry, described by a quantum group, which and in many cases we can obtain from the usual universal enveloping algebra with this simple choice by deforming the product or the co-product. And we will do the same thing here. And we see that the original trivial co-product in angle force trivial Yang-Mills is for any generator. The co-product is first act on first one or act on second one, keeping the other invalid. But now we change it to this one. Here it means that if we act on the first one, we have the omega j, which is identity if it's a unbroken generator. So because for unbroken generator, it's just like the previous result. We have the trivial co-product. But for the broken generator, we will use this omega j to shift the color index. And we can generalize this to the arbitrary length L of L particle state. It means that if we act on the L side of the particle, we keep the state before it to be invalid, and after it we shift the color index. And I should point out that this transformation is only well defined for open string states. Because if we change the color index, some states cannot be closed anymore. So this is the important point. Because in order to describe the symmetry, we cannot only focus on the physical Hilbert space of closed strings, but also we have to enlarge the Hilbert space to include these unphysical states.
Sorry, it is the same as that delta applied L times?
Yeah, basically, yeah, if you get this, and then you apply delta again, for example, on this, you see, if you get it here, you will still have G times omega J times omega J and something. If time here, delta identity is identity times identity. Do I need to write?
Okay, fine. And how about delta of omega J?
We assume that delta of omega J is still like omega J times omega J. And using this, it's also straightforward to check that the commutation relations are preserved after this co-product. For example, for each length L, if we consider this co-product, and they still have the usual commutation relation. And this can be done for all generators in SU4R. And actually, we will get something like this. Originally we have the algebra structure, and we have this further deformation by this C2 transformation. And I will denote by this U omega of SU2R to save space. Up to now, we have defined this algebraic structure. We still need to know whether this describes a symmetry of the theory. And in order to avoid the incompatibility of the non-trivial co-product with the cyclic or cyclicity of physical state, because you see that when we have a trace, it doesn't matter whether it comes the first, like we have x1, x2, x3, or x2, x3, x1, or x3, x1, x2, they are the same after the trace. But this co-product, it makes manifest whether it's in front of this or after it. So this co-product is not compatible with the cyclicity of the trace. So what we do is to cut open all the trace and averaging over the cutting point. So for every trace of some state like this, we have we average over it, so we have 1 over L, and we sum over all the place that we can cut. For example, from the trace x1, y2, xz1, we get 1 over 3 x1, y2, z1 plus y2, xz1, x1 plus z1, x1, z1, x1, y2. And if we do this for the action, it's very easy to show that the action of N2 theory is invariant on this.
Sorry, so before the action is a number, now it's a matrix.
Because the action is because the action you have the, for example, I don't have the M2 action, but for the M4 actions you yeah, you have some trace here, or like this. You have some trace. The point is that we do not want this trace. We always cut it open and write it as linear combination of open states, not closed states.
I still don't understand why that can be an action, because now it's a product of matrices.
Yeah, because like we regard every state as a matrix and by matrix.
Fine, but okay.
Yeah. The point is that although they are matrices, the way to act, because if you have a trace, we don't know which one to start.
Yeah, I understand that you have to cut it open for the action, the
Yeah.
action of this deformed quantum group
Yeah.
to make sense.
Yeah.
But then in the action of the theory, if you cut this open, how to make sense of the action? So before the Lagrangian is just a function, right? So now it's a matrix.
Yeah. The point is that we have trace of something, and what we actually see is that inside this is actually a matrix. These are the generator for each generator. Act inside this matrix is already gives zero, regard of this trace. We write it out.
Okay.
Since the action of this quantum group is only on this matrix, so that
Yeah.
and then this somehow they want to get this sequencing property from the just taking average.
Yeah.
Yeah, I guess I just don't understand, like, if you do this replacement, that would naively change the theory into something else, right?
Fine. Okay.
I have a related
The
question.
point is that if we have some, for example, if we have something like this in the action, and we act on this state, we will always get zero for every state in the action. Like this linear combination will give us zero.
Fine, yes.
Yeah, so and using this we show that the action, like this generator action is zero.
I'm not sure I understand, but maybe we'll talk about it later.
I have a related question. So, this cutting up chain is a bit like what Isaac was doing in dividing this PS2 to /2. And there was a central extension. After you do that, the symmetry is enhanced. I want to know what happened to the central extension if you in this other theory.
In this part we don't need the central extension because we only focus on asymmetry part. We don't see that. We will not see that for the asymmetry.
I see. So here you only focus on one loop scalar sure. Okay.
Yeah, maybe I should introduce, I should put a detailed calculation here, but it's a lengthy but straightforward calculation to show that if you expand out, if you write every term with a trace in action in this way, and you act on RAB, there will be piecewise, there will be pairwise cancellation.
I'm fine with that, but I just don't understand the meaning of the arrow. So you're replacing a number with a matrix. So in what sense is it allowed?
Yeah, the thing is we understand what you are doing, but we don't understand why it's legal to do that. That's my question.
So when you cut, do you break the gating arms?
Of course.
Of course.
Symmetry is associated with this cut. Not.
This action itself will change it will also act on the color space. So
There is not a true symmetry. A true symmetry, true group symmetry should be associated with gating arms.
there's no problem of gates in mind. This extra part does not act because we have SU2 times SU2. I said it's act on the color space because it changed the first SU2 with the second SU2. We do not change inside each SU2. So there's no problem.
But I think this case of operation, mathematically this operation is very similar to this, going from S, there is some well-defined map going from SG to the universal analysis.
But more interestingly is what happens if we move away from orbital point, because the result at the orbital point was already known long time ago. So we want to move away from orbital point, and usually and one may ask whether we will lose our symmetry, and actually the some examples in lower dimensions tell us that deforming the parameter does not always lead to throwing away symmetries. And here's the Heisenberg model, which everyone should know very well. And the symmetry of the system depends on the parameters. If we only work in the group theory framework, then if for the x-axis spin chain, where all the couplings Jx equal to Jy equal to Jz will have SU2. But for XSZ or XYZ, when the couplings are different, we'll break this SU2 down to U1 or no symmetry. But the true statement is that even for this case, we will have some quantum symmetry, quantum group symmetry or elliptic quantum group symmetry. So what we expect is that when we go away from the orbital point, we wonder whether we will have a further quantum deformation of our quantum symmetry. And we look at this is the one of anomalous dimension computation for the general kappa, and the result can be written in this way. Here we still have the projector into the singlet, the 15 and 20 prime. The eigenvalues are changed, and I put a hat here, meaning that the eigenstate is also changed, but it still have this structure. And similarly, for the open chain Hamiltonian, here we need to know whether I act on the first dynamical index 1 or 2 is related by kappa goes to 1 over kappa, and it also have this simple structure. You see that we have this projection of SU4, but this SU4 is different from the original one because it's the eigenstates and eigenvalues are kappa deformed. And this extra degeneracy indicates that a quantum SU4 symmetry exists even for kappa not equal to 1. And in order to describe this quantum symmetry, the upgrading of the generator of SU4 is the same as before, but the coproduct must be further deformed. Here, originally we put omega j here as their identity, but now we need to have more complicated coproduct. And we denote the resulting algebra by this. We put an extra kappa here. And it turned out that this k left and k right will depend on the dynamical index 1 or 2, and also depend on the representation. So in some sense, it's a non-abelian deformation of the original one. Here, I will give a general strategy to determine the coproduct. This will tell us that the coproduct always exists. We start with a common eigenstates of the conserved charge. Here for the open Hamiltonian, it's an eigenstate, and also and also for the other conserved charges. And in the limit kappa goes to 1, it should produce the result we get before. And for this, we have a preferred basis from N4 super Yang-Mills. Then the basis at generic kappa is related to the basis at kappa equal to 1 by this transformation matrix F. And using this F, we can write down the coproduct using this twist. So this tells us that this coproduct always exists. The problem is that this way is usually very complicated. And we can, here I will give some examples. First is the 20 prime multiply. We can work out all the eigenstates of this. And originally they are originally we have only SU2R and SU2 right, SU2 left, and they are related in this horizontal and vertical directions. But using the broken asymmetric generators, we can bring all them together. And a similar result can also be obtained for the open 15 multiplier. And most of these states will be quite complicated, so I restrict to the next one. We only consider the SU2 sector. In the SU2 sector built by X and Z, the open BPS states, this BPS is in the sense of angle 4 rather than angle 2. These states are not symmetric, because originally they are symmetric representations, but now they are not symmetric representation, but kappa symmetrized representations. These are the eigenstates of open chain Hamiltonian, and actually we can use the coproduct to relate them. And if we close, like, for example, we can look at 2x. We can, for example, close this state, x1, x2, x1, x2. We can close it by simply product trace. And for the other end, it's like z1, 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 z1. We can also close it by product trace. Originally, these two closed states are in different angle 2 representations, but now they are related in this way. And in order to relate them, we introduce some states like this x, 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 z, and x, z, z, z. These states cannot be closed. So in order to really see the actual symmetry, we have to introduce some auxiliary unphysical states. And for all this discussion about states, then we want to show that this is a symmetry. So we check whether it's whether action is invariant. And first, for the Taylor potential, the open chain eigenstate corresponds to the singlet is simply like this. It's not kappa deformed. And there's also another state by exchanging 1 to 2. And these states are precisely what we get when we cut open the Taylor potential up to some this gauge coupling factor. The effect of this is change the ordinary derivative to covariant derivative, but the gauge field is uh, a singlet under the asymmetry, so this doesn't matter. Therefore, from this we see that the Taylor potential is invariant under this deformed symmetry. And similarly,
so
we
here
can-
it's also like a, when you have a trace, you just
yeah, we
average.
can't open the trace. It's important to can't open the trace.
Okay.
Here, because here we have trace over 1 and trace over 2. Here we get Z1, Z1 bar Z1. And here we combine with this X bar 1, X2, and Y bar 1, Y2. And for the like Z bar 1, 2, Z2, we combine this X bar 2, X1, and Y bar Y2, Y bar 1. And these are two singlets. So in this way we get the we can build this closed state from this open state, and each term in like each open state in this decompensation is a singlet. So the Taylor potential is invariant. Then for the super potential, we also find this eigenstate. And actually, and there's also another one with one change 1 to 2 and kappa goes to 1 over kappa. They are in the representation 10 of SU4. And from this state and its and the other one with 1 to 2, they can combine into this super potential. If we cut over this super potential, we get this the linear combination of these two. And actually, if we decompose this 10 in the representation of SU4 into irreducible representation of SU3 formed by XYZ, it's 10 decomposed in this way. And these two states are in the singlet. Therefore, the super potential is also invariant. So we can combine the fact that the Taylor potential is invariant on this quantum deformed SU4, and the super potential is invariant on this quantum deformed SU3, with the fact that with the unbroken N-to-Y silver symmetry, we obtain that the whole action is invariant.
Sorry, do you think this symmetry is zero form or something?
It's therefore we here we always consider local as our local operators, so it's therefore. I never discuss extended operator in this course. So there's no
What if
hyphen.
you, in the beginning you do Z4, or you don't do some equals 1?
No, it's N1 or N2 depending on whether your orbifold
Right.
group gamma is inside SU2 or SU3 or SU4.
Yeah, I'm just curious if you choose some other discrete group, what you could have for the procedure.
Yeah, you will get. I will say. I will say it soon. So first, let me summarize what we have, and then I will try to conjecture some generalizations. So what we see is that we study a family of 4D angle 2 simple conformal field series obtained from angle 4 super Yang-Mills via orbifolding, and today only for Z2 orbifolding, and then doing the marginal deformation. In the planar limit, the naively broken generators of SU4 symmetry of the mother angle 4 theory are not lost but quantum deformed. And this quantum deformed symmetry are important to explain some extra degeneracy in angle 2 theory. And we also see that the action is invariant under this quantum symmetry. And the states can be organized in representations of this symmetry. And naively broken generators connect states in given angle 2 multiplets. And then we have the conjecture. First, all gauge theories descendant from angle 4 simple Yang-Mills will orbifolding or oranifolding and then doing a marginal deformation enjoy a quantum deformed SU4 asymmetry in the planar limit. And then we can embed this SU4R into the N4 simple conformal algebra GSU22/4. And then we should expect that all these series is like this have a quantum deformed N4 simple conformal symmetry in the plane limit. And there are still many interesting open problems. First, we study this hidden symmetry, mainly using the one-loop anomalous dimension. There are a large number of other observables, such as the all-loop anomalous dimension, the higher point correlation functions, Wilson loop, and scattering amplitudes, etc. And they should all be used to analyze our hidden symmetry in order to fully understand it. And second, for an ordinary global symmetry, there are standard procedures to describe various constraints, such as the Noether theorem, the word identity, the anomaly matching condition, etc. Similar results should be also possible to derive similar results from our quantum symmetry. And also it's interesting to see whether it's possible to apply our symmetry in a bootstrap program.
But is there an anomaly for this symmetry?
What?
Anomaly.
Up to now we don't know.
Well, depending on whether you can gate, so
Yeah.
gate
How
like
to-
the quantum gate.
We don't know how to really gauge this. Yeah, because it's very strange. It's the because you see the transformation is non-local. So this means that if you want to gauge it, it cannot be a local field theory.
Non-local gate.
Yeah, it's a non-local gauge. So I don't know how to do it. If you know, I will be really interested. And third, it will be interesting to find a string theory interpretation of this symmetry. We know that using M parallel V3 rings on like R3,1 times R6, we get angle 4 super Yang-Mills. And this R symmetry, SU4 R symmetry, is just the rotation of R6. And for the angle 4 super conformal field theory, we replace this R6 by R4 mod gamma times R2. And it's well known in mathematics that orbitals will naturally lead to group points. And this is why we see the algebra, the infinitesimal version is the algebra. So that's why we see the algebra structure. And if we want to perturb the coupling away from orbital point, we need some background B field, background NS B field along the two cycles in this space. And it's standard that background B field will lead to non-commutativity and therefore lead to quantum deformation. So it's interesting also to understand our symmetry from this string theory point of view. And also we can go further because we know that angle 4 super Yang-Mills in the planar limit not only has the simple conformal symmetry but also a Yangian symmetry. And this Yangian symmetry underlies many exact computations using the method of integral models in angle 4 super Yang-Mills. And it was known that if we orbifold the angle 4 to get angle 2 theory, at the orbifold point, it's also integrable, but away from orbifold point, it was proven like long time ago, it's not integrable by some people, also including here. But recently, it was shown that there's some loophole in this proof, and they wonder that maybe this angle 2 simple conformal field theory can also be integrable in the planar limit, even away from orbital point. And if this is true, then it's interesting to explore whether we can associate a quantum deformation of this Yangian, and also to these theories, to these orbital theories. And finally, it will be interesting to combine this quantum symmetry with other type of generalized symmetries. Thank you.
Questions?
So what's the evidence that away from orbital point it might still be integrable?
Because away from orbital, like at the orbital point, the one root, at the one root order, the anomalous dimension corresponds to a 6 vertex model. Away from orbital point, it corresponds to a 15 vertex model. And for that model, although it doesn't satisfy the Yang-Box equation, it satisfies the dynamical Yang-Box equation. So it's, yeah, but it was shown by further and others that the dynamical Yang-Box equation is more general condition for interval systems. The problem is that for the 15 vertex model, there's no one really solve it. So we don't know because we don't, as I explained here, we don't know the like Yang like structure. We don't have algebraic data on us, and for the quantitative data, it's extremely complicated. So it's reasonable to expect that it can be solved, but no one so far really solved it.
So it's a kind of useless integrability.
Yeah.
We claim there's a dynamic Yang-Box equation, but you can not really use it to do anything at this point.
Up to now, we don't know how to really use it. We just know that from the mass point of view, they claim that you have this.
At least are there higher conserved charges from this construction?
They can construct higher control charges.
Okay, so
But the problem is that for the dynamical Yang-Box equation, no one really classifies the solution. So, and for the first 15 vertex model we are using, it's not in the known solution. So
have you tried to diagonalize this 15 vertex model or the spin train directly?
yeah, this is actually what we did here. For all the Hamiltonian we get, for all the because as you see, for example something like this, for all this result we just directly diagonalize the matrix. But this way we can only do it for 2, 3, 4 sides. For 5 is almost beyond the computing power of like computers. So we really need other methods to solve it.
So are there some interesting degeneracies?
Yeah, we see this degeneracy.
I see. And also, are there some specific points of this kappa where things become simple?
Kappa equal to 1 reduced to the original case.
Okay, apart
For general kappa, I don't see any like actual simplification.
Because from say XYZ spin chain, there's an analogy when if you are at the root of unity for Q, then you can construct some eigenstate. But generic Q cannot do that. So I was wondering if there are specific points, at least you can go a bit further.
I don't know whether there's something.
Kappa text imaginary value.
For example.
Minus I.
Just looking for special point.
I don't know anything really.
Because you say you diagonalize it by brute force, so in this case you typically fix kappa to some numerical.
No, we solve it analytically. The problem is that you see here we have some twisted sector. If you go to number side, there are a lot of states in the twisted sector, and they are useless. But when you just diagonalize it, you have to compute it. So this will make things really complicated. So we really want to know whether there's a better way to do this computation rather than this brute force way.
And are there any tools we know?
No.
No.
Can you use this symmetry to, for example, simplify or reorganize certain known quantity index or so? Does it help reorganizing the states appearing in the
As far as I know, we don't know. Actually, this is the first time that this kind of symmetry appear in gauge theory, higher dimensional gauge theory.
You know, there are people in the literature discussing something like a bilocal symmetry or biform symmetry.
Yeah.
Is it kind of relevant?
Bilocal is more like at the level of Yangian.
Yeah.
We are still at the asymmetry part.
Yeah, but it seems like you're kind of dealing with some non-local or bilocal.
Yeah. Up to now, I think we don't really need that. Or if you want to say this is already bilinear, something like this. Okay, this is, if you want to say like this is already something bilinear.
Any other questions? If not, let's thank Xinyu. So lunch break, and then as usual, students will help you to at the canteen.